Hey everyone, welcome to Code Harmony. Today we are going to cover a very important concept in string, which is string matching. You are given a string and you are also given a pattern. You have to let me know that whether that pattern exists in the string or not. See, whenever we search a word in a Word document, we are able to get the result very fast. Why? Because there is a very powerful algorithm which is able to do it in a linear time, order of n time. So we get the result very fast, and that algorithm is known as KMP algorithm. We'll be moving till that algorithm in this lecture, but we are going to build the approach slowly. Here we are going to cover two major algorithms. First one is Naïve String Matching Algorithm and second one is our KMP for sure. So let's have a look on them one by one and see how the algorithm works. Our first algorithm is Naïve String Matching Algorithm. What does it say? Blindly checking all the possibilities. Okay, and the definition is compare the pattern with the string, or you can say text, one character at a time, doing in a brute force manner. And this algorithm gave us the time complexity of n into m, where n is equal to text.length, m is equal to pattern.length. Let's say if I run it over this example. Let me clear these pointers. Okay, in this case the text is ABC ABCI and the pattern is CAB. So what we do in this algorithm is that we have one pointer for this, one pointer for our text, and we check whether these two characters are matching or not. If they are not matching, just increment our I pointer and start our J pointer from 0 for sure, and then try to match the whole pattern, whether that pattern is starting from this index or not. Or in the next iteration, we see whether the pattern is starting from this index or not. If I just compare C with C, it is matching. A with A, it is also matching. Again, we are also incrementing the pointers. B is also matching. Now, if B is matching, my J pointer is going to come at M, which is the length of pattern. Length of text was n, length of pattern was m, and while matching, if the characters are keep on matching, we are just going to increment the I pointer and J pointer, and if the J pointer is becoming equal to the pattern.length, it means we have found a pattern at this position. If you have found the pattern, then you can just return whatever is requested. Let's say in this example, whether the pattern is present or not, yes or no. So you can return a boolean according to that. So here in this case, what is going to be the time complexity? For every pattern matching, we are going to start from this index, and if it is not matching at any moment, then start from next index, start from next index, start from next index, in this way. So we are going to start from every I, until which I we are going to get the pattern is of size 3. Okay, if the pattern is of size 3, at least we should have 3 characters in the matching from the text. So I should go till this moment. If the pattern is not present at this, it is not present. So I is going to be starting from 0 and going till n minus m, both inclusive. So this is the range for which I pointer is going to start, and for every I, the J is going to go from 0 till m. This is the algorithm, or you can say directly the code for this problem. I is going from 0 to n minus m, and J is going from 0 to m, and we are matching whether the character is same or not. If the character is same, then increment both the pointers. If the character is not same, break it and do a fresh starting. We are breaking it. It means I++. If in the previous call I started from I equal to 0 and at I equal to 3 it is not matching, then in the next iteration I'm going to start from I plus 1. I was 0, then plus 1. That's why I have taken another variable which is k. So let's work on this example. Let's have a detailed discussion on this example. Here we are having our J pointer. Here we are having our I pointer. It means we are going to start matching from I variable. And apart from that, I have also taken a variable which is k. Why k? because the next iteration is going to start from I plus 1. So I don't want to disturb my I. Both are at 0. I is also at 0. If k and j are not same, if k and j are not same, then break it. Breaking means incrementing I, and k is also initialized with I. Okay. So now we are starting from B and C. B and C are also not matching. It means we are going to increment I and initializing k with I, and then j is starting from 0. This is the state. If we have a look here, C is matching with C. If that is matching, increment k and increment j. K is incremented, k is coming here, j is coming here. They are also matching. Now k is coming here, j is coming here. They are also matching. K is coming here, j is coming here, and now j is becoming equal to m. J has become equal to the length of pattern, and now in this case what we have to do? We are going to have this case running. This case where j is equal to m, return I. That pattern is found. Pattern is found. Why I am returning from this? Because I just want to return whether the pattern is present or not, or if it is present, just return the first position. The problem can be of any form. Let's say return all the patterns. If it is all the patterns, we have to keep on searching and capturing all the value of I. So it means from I, we are starting from I equal to C. It means there is a pattern if we start from I equal to this. If we want to keep searching for next pattern, then in the next case we have to just increment I, and k will be updated to the new I. So in this case, we are going to compare this pattern starting every I, every valid I, and we are going to go till this moment, n minus m. Okay, so starting from every I can go around n number of times. For every n number of times, we are going to have a pattern of m size. That's why the time complexity is order of n into m, which is a quadratic time. But initially, we discussed that we are going to have a linear time to find a pattern in a text. So for the linear time, we have our next algorithm, which is going to be Knuth-Morris-Pratt KMP algorithm. Now we are going to discuss our second algorithm in string matching, which is Knuth-Morris-Pratt algorithm, KMP algorithm. From the previous Naïve String Matching Algorithm, we are getting a time complexity of order of n into m, which is very inefficient for long text or long patterns, because we are getting a quadratic time. Why? Let's say the text is this and pattern is this. If I just take a pointer and apply the Naïve String Matching Algorithm, I will keep on matching these strings, and at this moment I'm just getting a mismatch. And then what I'm going to do is I am going to start from this and comparing again, this comparing again, and this, and then comparing again. And starting from this, when I compare, all the characters are matching, and I get to know that at this E, it is not matching. A, B, C, A, B, A, B, C, A, B. So A, B, C, A, B are getting matched multiple times. So there are redundant comparisons. So we just have to match the pattern smartly so that we can avoid duplicate matching. That is the key idea behind KMP algorithm. So let's have a look on the definition. Efficient pattern. Efficient pattern and matching algorithm. Okay, we are doing it efficiently to search the pattern in the text in order of m plus n time. Okay, m plus n, which is linear time. Initially, we were having order of n into m time from Naïve String Matching Algorithm. Now we have order of m plus n. Length of pattern and length of text. Got it? And they are saying avoid unnecessary comparisons using LPS array. What is LPS? LPS is longest prefix suffix array. Longest prefix suffix array. So here in KMP we prepare some kind of LPS array. LPS array means longest for any string, which is the prefix, what is the length of the prefix which is equal to the suffix. We'll have that understanding later on. Before that, first of all, we are clear about these two statements. Efficient pattern matching algorithm. Okay, this is the time complexity. Avoid unnecessary comparison using LPS array. So every word is clear to us apart from LPS. Longest, prefix, suffix. Longest we know, longest. Prefix, suffix, let me tell you what is prefix and suffix. For any string, let's say this is the string, and in the string there are 6 characters. For this 6 characters, whatever is the substring starting from index 0, that is a prefix. Let's say in this case A, AB, ABC, ABCA, and many more. These are the prefix. And suffix, any substring ending at n-1 index, that is a suffix. C in this case, and then BC, ABC, CABC, BCABC. These are our suffix. Okay. So what is LPS? Longest prefix which is equal to suffix. In this case, if I just have a look on this prefix ABC, ABC also present in the suffix. And apart from that, if we just have a look on the other options, we are not going to see any matching. So ABC is a substring which is prefix and suffix of same length, and this is the longest, because in this case there are no smaller options, but there might be the possibility that we have multiple prefix suffix, but they are matching, but we have to choose the longest one. Here we have only one possibility of size 3, so ABC is our longest prefix which is equal to suffix. ABC. And how this LPS array is beneficial, we will understand that later on. Firstly, just do the understanding of LPS. Okay, LPS definition is also here. For any string, length of the longest prefix which is same as suffix. This is something that I just told you. Length of the longest prefix which is also the suffix. This is prefix, this is suffix, and length of this is 3. It means LPS for this string is equal to 3. So this is something we have to capture. LPS value for this string is 3, starting from index 0. Then how many substring we are going to have? 0, 1, 2, 3, 4, 5. We are going to have 6 substring. First one is A, then ABC, ABC, AB, AB, ABCA, and this much. If this is the string, if I just have a look, what is the length of prefix which is also equal to the suffix? Now if I just have a look on the string which is equal to A, for every string of single character, LPS is 0. For the string of 2 characters AB, there is no prefix which is same as suffix. So in this case also LPS value is 0. In the string ABC, it is also 0. ABCA. In this string, if I just check, this A is common as this A. Prefix A is same as suffix A. So the length is 1. In this case, I'm going to get 1. ABCAB. In this string, I can see that AB is matching. AB is the prefix and AB is the suffix. If I just have a look on any bigger prefix, then that is not equal to any other suffix. So the longest prefix which is same as suffix is 2. And in this case, it is ABC.
Enough juice.
ABC, which is 3. So what is this value? These are the LPS value of these strings. And whenever we are matching a pattern in a text, we are starting the matching from the j equal to 0. And if this is a pattern, then we always start from j equal to 0. That's why we are going to capture LPS value of every substring starting from 0. So let's have a look on this table. This table is going to have A. It means this is the LPS value of substring A. And this is the LPS value of substring AB. And this is the LPS value of substring ABC. and this is for ABCA, ABCAB, and this is the for. This is for whole pattern. Now this is my LPS array. We have verbally seen that, okay, how do we prepare it, and now let's have a look on an example. Let's say in this case we are going to prepare the LPS array for this pattern. The length of the text is n, the length of the pattern is m. If we are going ahead with the naive approach, the time complexity is going to be n into m. But let's try to see where we can do better. If I start from this j and this I, this is not matching, and we have to start our comparison from this I. This is also not matching. If I at c, this is matching. This is matching, and now just increment j and increment I. Increment j, increment I, increment j, increment I, incrementing j, incrementing I, incrementing j, increment I. Till this moment everything is matching. Okay, and when I value of this I is coming at this position, or j is coming at this position, value of I, or you can say value of k, is coming to this position, because we are starting our matching from this I equal to this. Let's say value of k is coming at this. So we started our matching at this position and this position, and when we are coming to this C and E are not matching. Then what we have to do? As per the naive algorithm, we have to start looking for that again, looking for the pattern again from I plus 1. But in this case, if we try to utilize the property where the prefix and suffix is same, and that is the longest, till this moment this pattern is matched, and in this pattern this CAB is the prefix which is equal to the suffix CAB. Okay, and my value of k is at this C. It is at this C, and this pattern is matched. It means this CAB is present at this location before k. Okay, and if this CAB is present at this text, this value is also a prefix. If it is also a prefix, then there is no need to compare that again. That means I can start matching from C again, and there is no need to change this pointer. Okay, CAB, longest prefix which was equal to suffix was CAB. It means CAB is also present in the text, because CAB, this is already matched. This character is not matched. This character is different from E, but this pattern, this CAB is also the prefix of this pattern. So this CAB, there is no need to compare that again, the CAB and CB. So utilizing this benefit where longest prefix which is same as the suffix, we are able to avoid multiple comparisons, similar comparisons. Now in this case we don't have to hamper our k pointer. Now my k pointer will remain at C, and I am updating my j pointer from E to C. Now the C is matched, A is matched, and now my k is coming here. K is coming here. B is matched, and this E is also matched, and again j is coming out of the pattern. J will become equal to m. If j is becoming equal to m, at this pointer, if I go behind j values, behind m values, I am going to get the starting position of the pattern. And if it is the case, just return, you can directly return true. Okay, got it? So in this case what I did is, when starting from index equal to 2, my pattern does not match on the last character, I am not starting from I plus 1. I will keep on going in the text. In the text, I will keep on going. I am not going back. So in the worst case, it is going till the size of n, which is the pattern length. But how we were able to move our j pointer to this pointer? That is because of the LPS array. LPS array, and LPS array we have to prepare in advance. So let's say for this pattern CAB, CABE, CAB, CABE, what is going to be the LPS? C 0, A 0, B there is no prefix which is equal to suffix 0. Now in this case there is one length prefix which is same as suffix 1, and in this case CA, in this case CAB which is 3, in this case CAB, and no, there is no prefix which is same as suffix, that is 0. So this LPS array you have to prepare first, and then you have to use that LPS array to search into the pattern. If you are not able to understand it, we are now going to see the concept of KMP step by step. Firstly preparing the LPS array and then using the LPS array. These are the two major steps. Preparing longest prefix which is equal to suffix value for every substring starting from 0 index, and then using it. Simple. These are two parallel steps. Firstly we have to do this, and then we have to do this. We'll have a look on them step by step. Let's prepare the prefix array, longest prefix suffix array, and from the pattern we have to compute LPS value for every substring starting at 0. So this value is of substring C, and this value is of substring CA, and this is the value of CAB, and so on. This is the algorithm for that. If I just have a look on the algorithm, initialize LPS 0, LPS 0 with 0, I equal to 1 and length equal to 1. Let me take this example. AB, AB, C, AB, AB. Okay. We are going to work on this example using this algorithm. Initializing LPS 0 with 0, index with 1, length with 0. These are the two pointers we are taking. While I is less than m, we are iterating over the pattern. If the value of I is equal to length, then increment length and update the longest LPS value and then I++. If it is not equal to, then we have to follow these two conditions. We'll have a look later on. Firstly, let's try to build our LPS array. We are going to start preparing our LPS array with this example AB, AB, C, AB, AB. Okay. This is our initialized state. Length and I, we are having two pointers. Length is pointing to 0, I is pointing to 1, and the LPS of 0 is 0. This is our initialized state from algorithm. Now value of I will go till m less than m. It means we have to iterate using I pointer, and we will update the value of length accordingly as per our need. Firstly, we are going to match value at length and value at I if they are same or not same. If they are not same, then I have to update length equal to LPS length minus 1. Use previously computed LPS value. Okay. If the value of length is greater than 0, I have to perform this operation. Otherwise, LPS of I equal to 0, increment I. So in this case, length and I value are not same. So LPS of I is 0 and increment I. I is incremented. Now we have to compare I value and len value. Both are A in this case. If both are same, then what we have to do is we have to follow this statement. Increment length, set LPS I equal to length and then I++. Firstly, we have to increment length. Incremented length, updated LPS I value with the length which is 1, and then incremented I. This is the previous I. This is the current state. Now we have to compare an length with I. Length and I both are same. So LPS I is equal to length plus 1, which is 2. Now the length will be at this and I will be at this. At this moment, L and I are not having same characters. If they are not having same characters, what I have to do is also the length is greater than 0. length is pointing to 2, which is greater than 0. So length will be updated to length L minus 1. This length is pointing to 2. So this will be updated to LPS of length minus 1. LPS of length minus 1 is 0. So this will be updated to 0. So the length is coming to 0. And now I have to see what is going to be the value of LPS I. Length is 0. It means LPS of I will be 0 and increment I. LPS of I is 0 and increment I. This is the state now. Now I have to compare L and I again. L and I are both having same characters A and A. So L length plus 1, which is this, and then update the value in LPS I and then increment I. I am doing whatever is written in my algorithm. You might also have to dry run for 1-2 times, then you will get the understanding. Okay, now L and I both are having same value. Increment L, update the LPS of I with L, which is 2, and then increment I. Now try to match the value at L and I. Again they are same. So length plus 1, which is 3. Length is going till this and 3 is updated here. I is coming here. State is something like this. See, what does this 3 mean? It means that starting 3 index and the last 3 index are same. ABA and ABA. Okay. And this L is specifying that what prefix is same as the current suffix. Now let's see our last case, which is L is pointing to 3, I is pointing to 8. Value at both the index are B. So increment length, update the value of L in LPS I, which is 4, and then increment I. Now the condition is I less than M is getting failed and we have our LPS ready. So this is the code for LPS finding or preparing the LPS array. See, the preparing LPS array itself is a concept that can be used to solve other kind of problems. So in this case, what I'm getting is that for every pattern prefix, I am getting the value of LPS. For every substring starting from 0, or you can say for every prefix, I know what is the length of prefix which is equal to the suffix. Now from this example, just pick any of the random value. Let's say I picked this 2. It means I am picking the value A, B, C and AB. In this case, the value is 2. It means these two values are same. And none of this is the biggest suffix and prefix. If we try to increase that, we are not going to get the same result. So that's why 2. It means if something is not matched at this, we are not going to start again from this value. We are going to start matching it from this because these two are already matched. This is the idea behind LPS. Now one part of the problem is done, preparing the LPS array, and the second one is if we have prepared something, we are definitely going to use that. Definition is quite simple. Searching pattern in text. That is our requirement using KMP. But using LPS, we will be able to avoid redundant matching. This is the algorithm for LPS. Start matching every character of P pattern with the text. If they are matching, then increment the pointer in both the text and patterns. And if we keep on incrementing and j is becoming equal to pattern.length, then we have found the pattern at I minus j index. If it is not matched, then there are two possibilities. If j is equal to 0, it means we have to start matching from the starting again. Otherwise j will not go to 0, j will go to LPS of j minus 1. The same thing that we did in our LPS preparing array at this moment. Use the previously computed LPS array. And this is the step which is helping us to avoid redundant checks to make the algorithm run in linear time. Now let's come to the example. First step is preparing the prefix array. Let me mark the indices 0, 1, 2, 3, 4, 5, 6. If I just get the prefix array, what is that? Prefix array should be 0 and CA it is 1, CAB it is 0, and this C is matching with this C 1, 2, 3 and then 0. You can pause the video and see whether it is correct or not and how I have prepared it, because it was pretty simple. Now we will start matching this pattern in text by using pointers. One pointer is pointing at J and the second pointer is I. And if these two pointers are matching, I and J are matching, we will just increment both. Otherwise what I am going to do is I have to update J to shift to backwards to start searching again. But I pointer will only move forward in this case. I pointer is not going to come back. That will help me keep the algorithm linear. So this is not matching, increment I. This is also not matching, increment I. This is matching. If this is matching, then what I have to do? If this is matching, then I have to increment this and this as well, both the pointers. I is coming here and J is coming here. Okay. Now what is the next pointer? Next item is A and A. This is also matching, increment both. Again, next is also matching, increment this, increment this, increment this, because they are matching. Now when I'm coming, I is coming here and J is coming here. At this moment, I'm realizing that the pattern is not matching. If the pattern is not matching, then we have to utilize our LPS array. LPS array that we have prepared in our first step. Now, the I pointer is not going to come backward. I have to see whether at what moment I have to keep my J. It means till this CAB, this string is present in this. And for this string, what is the LPS value? LPS value is present at this moment and this value, right? Because B is at this. At this, the LPS value is 3. It means for this string, for this substring, there is a CAB which is equal to CAB. It means the CAB will also be there. If the CAB is present here, it means that is already matched. CAB is already compared, and if I just jump our J to this value, 3 value, then I can start my comparison from this updated value of J. So now what I have done, in short, J is becoming equal to LPS of J minus 1. J is equal to LPS of J minus 1 if J is greater than 0 as per our algorithm. So in this case, what I have done is I have avoided 3 redundant checks, CAB and CAB. Now we can start matching again. If I have updated my J, so J is currently at this position, I is currently at this position, C is matching, great, move ahead, A is also matching, move ahead, B is also matching, and this E is also matching, and then J is going out of bound and I is coming here. At this moment, I am realizing my J value is becoming equal to M. That is, I have found the pattern and written yes from the pattern. Great. So now you have achieved this algorithm. I is going from 0 to N. In order of N time, you have achieved this solution. You have, in the order of N time, you have achieved the pattern matching. If you have LPS array, if somehow I give you LPS array, in the order of N time, you can just achieve that. Now, what is the time complexity for preparing LPS array? That is order of the length of the LPS array. Okay, so this is our KMP algorithm, and now the algorithm is attached here. I will also attach the notes in the description below. These two algorithms are very important. Now let's do the complexity analysis. Complexity analysis of our KMP. The Naïve algorithm you already know, n into m. For the KMP, first step is preparing LPS array. Second step is using LPS array. Preparing LPS array is order of pattern.length, and this step is our pre-processing. We have to do this pre-processing before we are starting our matching logic. Okay, now what is the search time? Search timing is order of n, which is the length of text. Length of text, length of pattern. Overall, it is order of n plus m. Length of text plus length of pattern. In short, it's a linear operation, linear time complexity, but we have some pre-processing that we have to do before we start matching. Firstly, let's have a look on the advantages. Avoiding unnecessary comparisons. Okay, how it is avoiding unnecessary comparisons? Using LPS array. So avoiding redundant operations work well with the repetitive patterns. When the pattern length is very big and there are repetition in the patterns, then it is working fine. Linear time complexity, great, that is awesome. That's why we are able to find any word in the Word document quite fast. Efficient for large text. If it is a linear time complexity, then we don't have to worry about large number of test cases. Let's come to the disadvantages. Pre-processing overhead. Pre-processing is something we have to firstly prepare the LPS array. Not suitable for single or short pattern. Let's say the pattern is AB. For the pattern AB, what is the LPS array? LPS array is 0, 0. It is useless for us. That's why this is not good when we have to just find AB in the pattern. So these were the advantages and disadvantages of our KMP algorithm. Now let's come to some real world application. Word processor. In MS Word, Sublime Text, Vim Editor, we are able to search the pattern using KMP algorithm. Plagiarism detection, copied text detection. That is something we do with KMP. DNA sequence matching in bioinformatics. That is done using KMP. Spam filtering in email is also one application. So there are so many famous applications for KMP. And now here comes to the end of this KMP algorithm. When I was in graduation time, I used to find it very difficult to understand. So I used to just cram it before every interview. But now I think you will be able to understand the exact idea behind this algorithm. Now we'll have a look on the Java code for this algorithm. First of all, let's have a look on the Naïve pattern matching algorithm, where we are going to get the pattern in the order of n into m time. We are going to utilize. We will be doing it using two pointers, one pointer for text and one pointer for pattern. And what is this value of k? Start from k this time. We are firstly starting matching from k equal to 0 in the text, and then in the next iteration start from first character, and then in the next iteration start from second character. It means we are going to start from every single character in text for the whole pattern. That's why it go m into n time. Text and pattern, if both are same, increment both the pointers. If they are not same, it means there is no need to move ahead with the pattern matching. Start the pattern again from 0, increment the value of k, and this time reset the value of I with k. This is the Naïve algorithm. Now let's come to the KMP algorithm, for which first step is prepare the LPS array and then use the LPS array. LPS array is definitely going to be the same size of pattern. Length is 0 and I is equal to 1. So this is our initializing state. Length should be 0, I equal to 1, and LPS 0 is already 0. If pattern I is equal to pattern.length, increment the length, update the length into LPS I, and then increment I if they are same. If they are not same, then update the length pointer to LPS of length minus 1. This is something using the LPS array, using the pre-computed LPS array again. If the length is 0, If the length is 0, then LPS I is also 0 and increment I++. I is always getting incremented. This is for preparing the LPS array, and now we are going to use the LPS array. LPS array we are able to get, and then using 2 pointers. I pointer is for text, which is always going to increment, and J pointer is for pattern. Whatever condition is failed, we are just going to come out of the while loop. If they are same, keep incrementing both the values. If they are not matching, update the value of J. Here J is coming to LPS of I-1. In the naive algorithm, J is always coming to 0. In this case, J is coming to LPS of J-1. Why? Because till this moment, we have already compared. We are avoiding redundant comparisons. And yeah, I should always be incremented. This is using the KMP, using the prepared LPS array. I'm also going to attach the link to this file in the description below. You can just have a look and just try to do a dry run on pen and paper. You will get very good understanding on this algorithm. Thank you guys. Bye bye. Thanks for watching.